All right, so we're going to start talking about quadratic reciprocity, which is an entirely new topic, which we haven't talked about before. And let's start with just a, I hope, surprising pattern. So suppose you have the number 4, and you ask, is it a square modulo p? Pretty easy to answer, right? What's the answer? Is 4 square mod 5? It's not very hard. Raise your right hand if you think 4 is a square modulo 5. It is 2 times 2, so it's probably a square modulo 5. So it's already a square, so it's obviously a square modulo 5. Is 2 a square modulo 5, though? No, because you could just take all the numbers mod 5 and square them, namely 0, 1, 2, 3, and 4, and the numbers you end up with are 0, 1, 4, and 1, or minus 1. I just got confused. Okay, if you square the numbers mod 5, you get 0, 1, minus 1, 3 squared is minus 1, and then 4 squared is 1. So you just get 0, 1, and minus 1. And that's it. And in particular, you don't get 2, and you don't get 3 either. Okay? So some numbers are squares mod 5 and some aren't. So now you can take, let's take the number 2. Let's ask the question, when is it a square mod p? So if you take p to be 2, it is. If you take p to be 3, is it or not? Nope, it just isn't, because you can check and it isn't. You could take 5 and we just check that it's not. You could take 7. Is 2 a square mod 7? So it's a perfectly clean question to ask. Maybe it is, maybe it isn't. How can you answer it in particular cases? What? Yeah, so definitely, without knowing anything further, everyone here should know that you could answer that question for any particular prime by simply computing all the squares and checking. This would obviously be a very bad approach if your prime was big, but it would work. So does anyone here have any just like ideas off the top of their head about how you might tell whether or not 2 is a square mod p, even if p is kind of big? Like, is there anything you can even think of beyond just squaring everything?
Sure, there's a sage command. Maybe it is underscore squared.
Yeah, there is, and it will tell you. But what is it doing?
I just read it up.
No. We're going to use it in a minute just to see if there's any patterns. But
probably has something to do with what it's convert to. Modulo.
Yep. So you could start by taking 2 and reducing it modulo p, but that's already just 2, so that doesn't help much. How would if you take a number like 17 and ask for its square root in the real numbers, how does that work? Does anybody have any idea how to compute square roots of real numbers? It's the sort of thing that I guess probably used to be standard in high school, and then they got rid of it because they had calculators. But you seem to want to raise your hand.
It's a process that's similar to long division. Take a guess of a number smaller than that. So, for instance, 4 is going to be 16. Subtract that to get 1.
Mm-hmm.
You drop down the number that you have at the top of the quotient, so to speak, and then append the digit that remains, and then append that as a number to 41 times 1. Just continue the process from there.
So to be fair to characterize that as you get the first digit, and then you do some iterative process and you get the next digit in decimal. You do some iterative process and you get the next digit in decimal, basically. If you know about like Newton's method, which you probably all do from calculus class, you can use Newton's method to find a root of a polynomial, like the polynomial x squared minus 17. A perfectly good polynomial. You take an approximation for a root, you do something with the derivative, and you get a closer root. And you just repeat this over and over again, and each time you do it, you get a closer and a closer and a closer root. And so you never get, the exact square root of 17, but you'll get a decimal approximation to it. If you try to do exactly that with numbers modulo, 37, it doesn't work at all because there's no notion of closer, and there's only 37 different numbers there, and the iteration doesn't really make any sense. So the analog of Newton's method doesn't make any sense modulo. You could try it, but you just end up bouncing around, kind of getting nothing. So, any other ideas? We'll return to this question, but the problem of computing a square root is actually surprisingly hard. I think in general it's an open problem to give a polynomial time algorithm to do it, mod p. For some primes p it's easy, but for some primes p it isn't. So actually finding a square root of a number mod p isn't necessarily easy. Though if you assume the generalized Riemann hypothesis, there are approaches that do make it easy. So you have to assume some big conjecture about the zeta function, weirdly enough, and that will make it easy. But we'll come back to that. The other question is a number a perfect square or not? So when you think about integers, basically, how could you tell, if I just wrote down a 20-digit integer, how could you tell whether or not it's a perfect square? Or even 1,000, let's say I write down a 1,000-digit integer. What would you do to decide whether or not it's a perfect square? What approach might you take? Like if I just take this integer right here, zz dot, or is it rand range? It's just going to be 1,000 random looking digits. That's actually not going to work. 1,000. Okay, is that number a perfect square? Is that something we can quickly decide, and how would you do it? It's 1,000 digits, so you're not going to type it in. Sorry. But let's say your calculator worked with 1,000-digit numbers. What would you do? Take the square root. You can very efficiently, via this iteration, just take the square root. And if you get it up to about 500 digits, you'll get a couple of .000. If it's a perfect square, you'll get number .0.000. Just take that integer, the part before the decimal point, and square it, and check if it's this or not. That'll tell you whether or not this number is a perfect square. So if you have an integer, even if it's very big, there's an efficient way of deciding whether or not it's a perfect square. Okay? And of course, it's highly unlikely that this number that I made up at random is a perfect square. Because, well, let's see. So n gives you a numerical approximation to that thing, let's say with digits equals 700. There should be a decimal point somewhere in there. Oh, scientific notation. I want more digits. Make me feel better. Yeah, see, if it were a perfect square, it would be a lot of zeros at the end, but it's not, so it's not a perfect square. Simple as that. Okay, so then the question is there an easy way, is there any way to decide whether or not, say, the number 2 or the number 3 or whatever, say number 2 is a square mod p? Okay, to be very concrete, let's see, is 2 a square modulo, I want a big prime, so next probable prime 10 to the 1,000. Okay, so we'll get a big prime, 1,000-digit prime right there. There it is. Is 2 a square modulo that p? Okay? I hope that at this moment in time you don't know how to answer that question, but in 5 minutes you will. Okay? And you'll learn something today. Hopefully. Okay, so that's a motivating question. Given some huge prime, can you decide whether 2 is a square mod p? The answer is yes, we can decide. I have no idea what the actual answer is, but we'll find out soon enough. Yes, you can decide. And so here's what we're going to do. We're going to decide based on flaky playing around with small numbers and then guessing what should happen. And then there's going to be a pattern which we'll be able to prove eventually holds, but we won't be able to prove it right now. But let's just look at what happens. So you want to decide whether 2 is a square mod some enormous prime number, and you really have no idea where to begin. So this is a typical kind of thing that happens in math. And let's do something else. Let's take the primes up to 100 and just ask whether or not 2 is a square modulo each of those, and see if there's any pattern. Okay? Try not to give it away too much. Obviously, there's going to be a pattern, but I'm taking the number 2, and I'm reducing it modulo each prime, starting at 3 up to 100. And it says false if it's not a square, and it says true if it is a square. Okay? So that's what I just did. I made a table like that. And there is a pattern here. So one pattern seems like it's true half the time and false half the time. Okay? So at least, I mean, that seems kind of reasonable. So that's something you notice. So at least you could say maybe there's a 50-50 chance up here, which is not very helpful at all. But do you see any patterns? Let's see. Any patterns at all? What? One trick when you see stuff like this is you could take numbers where it's true and take their difference and see if there's anything happening there. And other stuff. I mean, you just kind of have to look at it. Maybe you'll see a pattern. But in this particular case, I'm just going to do I'm going to put a little bit of extra information. I'm going to put p modulo 8 here. Okay? And I'm going to make the table have 3 columns, and then I'll ask, do you see any pattern? Okay? The only thing I've done is I've changed it, so now you can see what each prime is reduced modulo 8. Now do you see any patterns at all? It should be easier to see something happening.
The true ones are convergent to 1 or 7.
There you are. The true ones are plus or minus 1 mod 8. And the false ones are all plus or minus 3 mod 8. That's kind of nice. Now think about the question that you didn't know how to answer only 5 minutes ago. Namely, is 2 a perfect square mod this 1,000-digit number?
Why did you just take mod?
Yeah. It's pretty easy to take that 1,000-digit prime and reduce it mod 8 and see what you get. Let's take p mod 8 and see what we get. It's 1, so what does that make you think? It's true. It should be that 2 is a perfect square mod that enormous prime. Now, we haven't proved that. This is just a pattern that appears to hold for the primes up to 100. It's just a conjecture we're making that when p is plus or minus 1 mod 8, it is a perfect square, and when it's plus or minus 3 mod 8, it isn't. But that's reasonable, given the data. And if it's right, if this observation's right, then that allows us to say definitely 2 is a perfect square mod that 1,000-digit prime. It doesn't tell us anything about what the square root of 2 is, or a square root of 2. Like mod that 1,000-digit prime, it might still be incredibly hard to figure out what an explicit square root of 2 is. Some number mod that prime, probably be like almost 1,000 digits, and when you square it, you get 2. We don't know how to do that. But we do know that it's going to be a perfect square. Okay? And what if I just, let's just do this whole problem again for practice, but with 2 replaced by 3. Okay? So, is 3 a square modulo that humongous number p? You say no. I don't know why you say no, but you say no. The answer is either yes or no. So if you're, I'll put a yes, by the way. What should we do? Any ideas for something to try? I mean, I've kind of suggested a strategy here. Look at some data, try to see a pattern. Extrapolate from that pattern.
Are we going to take p mod 6?
Maybe. Let's see what happens. I want you to see what I wrote there. So let's do, no. I hit the wrong key. Oops. Okay, wait. I keep using Control instead of Command because I was using a Chromebook this morning. Okay, so here's what the raw data looks like for, let's see, starting at the prime 5 and going up to 100 and asking whether something is a square, and then you suggested looking mod 6. See if this works. Okay, so here's some data. Does it work or not?
Because mod 5 is false. And true.
Yep, so 6 is not the thing to take p modulo. Good guess. Any other ideas? Speaking of how powerful it would be if you can just figure out the right thing to take modulo. Let's try 12, okay? How does that look?
Looks like 5 and 7 are false.
Yep, that looks really good. So, going back to our 1,000-digit prime, which, I just realized that I named it p, but in the for loop I used a p. and hence we don't actually know the answer even to the other one. I overwrote my p by accident. So right here, I thought I was working with that 1,000-digit prime, but I was really working with 97. So let's just go back and answer the first question. I'm going to call the prime q. It's the same prime because it ends with 453, right there. And now let's see, is 2a squared modulo q is 3a squared modulo q. So to decide whether 2 is a square mod q, oh, it's 5 modulo 8. So what does that mean? False. So actually it's not a square modulo q. It isn't, sorry. So now what about 3? So we wanted to work modulo 12. Okay, well, let's see what we get. We get 1 modulo 12, and then looking at our data, that means it is a square. So is it a square modulo q? Is 3 a square? Yes. But just like with, say, primality testing, remember where we could test a number to see whether or not it was prime using Fermat's little theorem, things like that? You could decide, yes, a number is prime, or no, it isn't, fairly efficiently, but you can't actually factor the number efficiently as far as we know. Similarly, here, it's not, at least given what we know so far in this case, we don't know an actual square root. We just know with absolute certainty, modulo the fact we totally are conjecturing that this pattern continues, that it is a perfect square, but no idea what it is the square of, or what its square root is. Okay. All right, so is anybody lost? Does anybody have any questions? Just doing I'm basically just pointing out some things involving modular arithmetic and a pattern.
So are you going to prove something that on the side is square?
Yes. Yes, so now let me tell you some precise mathematical things that we will prove. So here is a surprising and non-trivial theorem. Whether or not a number a is a square modulo p, where let's assume p is an odd prime. This whole problem is very easy when p is an even prime, namely 2. It only depends on what p is modulo 4a. So when you're coming up with a number to work modulo to look for the pattern, it's 4 times a. 4 times 2 is 8. 4 times 3 is 12. Okay? So that's it. Deciding on whether or not a number is a perfect square mod p is equivalent to looking at, is it, like there, you have to do something, but the something you do is you take p modulo 4a and you'll find a pattern. So if you wanted to decide whether 17 is a perfect square mod p, you could figure out what happens with p modulo 17 times 4. In other words, you can make a big table taking your primes and reducing them modulo 17 times 4. And if you see a pattern there, this theorem right here says that that pattern holds forever for all primes. The main thing I want to convey to you, which is really difficult, is just that this is really surprising. It's just weird. I mean, think about it. What the heck? It's really strange that you can decide whether or not a is a square mod p by taking p and reducing it mod a multiple of a. I mean, why in the heck would anything like that actually work? It should seem weird and like there's just no reason for it. That's how it should seem to you. I mean, there is a reason because you can prove it, but it should feel surprising. Okay? Does it feel surprising, at least?
Jack and the beanstalk.
Yeah, I mean, it doesn't, like, why? It's just weird. It's just like in a totally different direction that you wouldn't expect. I mean, it must have been particularly interesting to Gauss when he observed Gauss, Legendre, these people hundreds of years ago, and they observed this because a priori, they didn't have any reason for this, no proof of any of this, but they just looked purely working with, pen and paper, or pencil and paper. I don't have to use pencils back then, but whatever they wrote with back then. They just looked and they found that, whoa, they made a table like we made, and they saw a pattern, and they're like, gotta see why this holds. I have no idea why this should happen. But it does. And just to codify what we're doing a little, Legendre introduced a symbol called the Legendre symbol, and here's what it is. It just kind of makes it easier. Instead of saying a is a square modulo p or not, you can encode that entire thing in one simple notation. This is annoyingly confusing notation because it looks exactly like a divided by p with parentheses around it. right? It looks like the fraction a divided by p, and you've grouped it. But what it means is, this symbol right here represents either 0, +1, or -1, as defined right here. It's 0 if a is a multiple of p. It's +1 if a is a square modulo p. And it's -1 if a is not a square modulo p. The words quadratic residue and quadratic non-residue, I did not define them on the slide, but quadratic residue means is a square, and quadratic non-residue means not a square. I'll change it, so a square equals not a square. And the theorem that I pointed out above, the thing I stated, which we haven't proved yet, but we're going to get to. And by the way, the proof isn't so easy, and very surprisingly is going to involve, well, this and other things. It'll involve sums of roots of unity. So you'll see. The above theorem is the statement that this symbol a over p only depends on p mod 4a. So that's just an equivalent statement of what we just did. Okay. And in Sage, there's a command Legendre Symbol, which you give it as input a and p. The first input is a and the second is p, and then it gives you back a number, either 0, -1, or +1. So let's just compute it for a moment. So there you are. Okay. So these are some values of the Legendre symbol. Okay. Now, that's not all there is to this. There's a theorem which is pretty amazing. I'm going to skip this for a second and state this theorem. This is the theorem that we're aiming towards. I'll go back to the stuff I just skipped. This is called Gauss's law of quadratic reciprocity, and this is the main thing that's proved in the book, for example, and it's one of the most famous theorems in number 3, and there's like well over 100 different proofs of it. And this one statement is really a special case of something called class field theory, which is in turn a special case of a huge amount of modern stuff, such as the modularity theorem, which you're doing your paper on. So it's really like right at the center of a lot of the driving work in number 3. But it looks really clean and simple. It's the statement. So remember, this notation, p over q, is defined whenever the denominator is an odd prime, and that's it, that's the condition. So if you have two distinct odd primes, here's the amazing thing that happens. Both sides of this equation are a number that's either 0, -1, or +1. And actually, either side is 0 because they're distinct primes. So this is a number that's either +1 or -1. That's a number that's either +1 or -1. And if you throw in this power of -1, since p and q are both odd primes, p -1 over 2 and q -1 over 2 are both integers. So you have a -1 here unless either one of these is 1 mod 4. So otherwise this is -1, because otherwise these are both odd. So basically, it's very easy to decide whether this is -1 or not. And then you have this relationship. But this is pretty striking because it says that you can figure out whether or not p is a square mod q by just throwing in the sign and then asking is q a square mod p. But think about it. Let's say that p is 3 and q is that prime with 1,000 digits. Deciding whether 3 is a square mod q seems, without noticing some pattern or whatever, seems pretty daunting. But deciding whether or not the 1,000-digit prime is a square mod 3, that seems easy, because you just take the big thing and reduce it mod 3. So really, what this says is all you have to do, if you want to decide, if your thing on the top, A, is a prime, like 2 or 3, then you just take the big prime and reduce it mod that thing. And then you also have to take into account some extra sign given by this formula. So this is an incredibly clean statement. You can also rearrange it in various ways if you want, because all the numbers involved here are +1 or -1, like the actual values. So if you wanted to put this one on the other side, so it's the symbol q over p times the symbol p over q is -1 to the p -1 over 2, q -1 over 2. That's of course equivalent, since You can multiply both sides by -1 and it doesn't change anything. So there's lots of ways of rewriting it. And by the way, there's some extra things. So whether or not -1 is a square mod p, there's a simple formula for that. And whether or not 2 is a square mod p, there's also a simple formula for that. And moreover, this is where it gets even better. If you consider the symbol, say, a over p, if you write a times b over p, that's exactly the same as a over p times b over p. So it's multiplicative in the numerator, which is what we're going to prove next. Which is not so easy to prove, but we'll prove that. Okay, so that is Gauss's law of quadratic reciprocity. It is a very nice theorem. It's relatively deep, but provable in this class. And at its heart, it just very, very systematically answers the question we started with today, which is how can you figure out whether or not some number is a square modulo some prime? Okay? And remember again, it doesn't give you a square root. It just tells you either yes or no whether or not a number is a square. But it's really better than just a yes or no. It's like a relationship. It's a reciprocity law in that it relates how P behaves mod Q to how Q behaves mod P. And these sorts of things like that are very surprising. It's a link between two very different things. Because somehow there's like a whole world of stuff mod Q and a whole world of stuff mod P. And one's way over here and the other's over there. And surprisingly, you can leap between the two. And you can take a question about, is 3 a square mod 1,000-digit prime, and turn it into a question of, is this 1,000-digit prime a square mod 3? Which is way easier. Okay? So that's the point and why this is interesting. Here's another little example just to kind of play with this theorem for a second. And it's nice because you can do this entirely in your head pretty much, or by hand. So you can ask, okay, I wonder if 5 is a square modulo the next prime year, which is 2017. Is 5 a square modulo 2017? So again, at first that seems hard to answer, and you wouldn't want to have to look for a pattern for what happens mod 20, like with primes mod 5, but you could do that. But what this says is that the question is 5 is square mod 2017. That's set P to 5 and Q to 2017 is exactly the same. So that's +1 precisely if this other side is +1. So you take -1 to the P minus 1 over 2 times Q minus 1 over 2. Well, 5 minus 1 over 2 is 2. Minus 1 to an even power is +1. So this whole business with the -1 right here, this just goes away. And this isn't some funny symbol where I forgot to put the parentheses in. It's just -1 to the power of product of two integers. So the second either one of these is congruent to 1 mod 4, this just vanishes from consideration. So the question, is 5 a square mod 2017? It's exactly the same as the question. As it turns out, is 2017 a square mod 5? But reducing a number mod 5 is really, really easy, because it's just determined by the last digit. So that's the same as, is 2 a square mod 5? And you know the answer to that. It isn't. So we didn't have to use a computer or anything to answer this question, which I'm sure at the beginning of class today, you would have been completely stumped by. If I had handed out a piece of paper and said, is 5 a square mod 2017? And I said, figure it out on paper, and you get a bad grade if you don't, then probably everyone would have been very annoyed. But now you can easily do that, right? So you learned something today. Okay, so let me pause for a second and wait for a question.
So 2017 is not a square mod 5 because you reduce it and get to 2, and 2 is not a square.
Exactly, yeah. Because whether or not a number is a square mod p just depends on the equivalence class. It depends on the equivalence class of that number mod p. So you can take that number, reduce it mod p, and it's the same question again. Sure. The definition of the Legendre symbol, right here, yes.
So in this one, so we know that that symbol is equivalent to 0 and +1 or -1
Yes, by definition, yeah.
By definition, but we need to still figure out what are the, so if A is a quadratic reciprocal or not.
Right.
And that's gonna, so is there a clean way to decide whether this is a reciprocal or not with given A?
So there's there are at least two algorithms. One of which I can't explain yet because it requires a little more work. But there are two ways you can decide whether this is +1 or -1 or 0. So let's say you want to compute this. That's what you're asking about, I think. So here are some approaches to computing this. We just did an example of computing this below. We computed 2017, right? So if you want to compute this, here are at least two things you can do. One, you can take your symbol and you can factor the numerator, which may or may not be doable in practice. So you can factor the A, and it turns out that this is multiplicative in the numerator. Remember multiplicative functions? So if you write this A as B times C, then the symbol A over B P is the same as B over P times C over P. I will prove that. That's actually the next thing. The thing I keep skipping over is exactly that statement. So once you have that, you factor the numerator, then you have a bunch of primes, and then you can apply quadratic reciprocity repeatedly. And what you end up with is, if you have Q over P, and you reduce Q mod P, so that makes Q less. That makes it so you have a question where it's less than P, and then you factor the numerator. So all the numbers there are smaller than P. Then you flip it over, and P is bigger than all the numbers, so you reduce P mod all of those. And you just keep repeating this process, and eventually your numbers will get as small as you want, and hence you'll be able to do it. Unfortunately, you have to factor in order to get going. But assuming you can factor, like your numbers are small enough to factor, that will work. Okay? Second, the group of non-zero numbers modulo P is a cyclic group. And that is the next actual thing we're going to prove in this class. So that means that there is a, given any prime number P, there's some number G, like maybe 2 or 3 or something, so that every number mod P is a power of that G. This kind of comes up in Diffie-Hellman, for example, where it's nice to have a generator for the numbers mod P, multiplicatively. So what you can do is, it turns out that a number is a perfect, well, using the cyclic structure, you can decide whether or not a number is a perfect square by simply raising it to the power of P minus 1 over 2. This, on the right-hand side, is just a to the power of P minus 1 over 2 mod P. Let me write that right here, because that's kind of shocking and surprising. What do you think of that? Okay, I want to typeset it with math so that it's clearer. So you may or may not think this is awesome, but there you are, assuming that A is coprime to P. So, and I put -1 there, which makes no sense because it doesn't even depend on A. So actually, you don't need to assume anything. So there you are. And this is all mod P, so P mod P. Just emphasize that. So look at that. So depending on your perspective, you may or may not think that this is really good. But remember, it's easy. You can efficiently compute large powers modulo P. Right? This is the sort of thing we know from doing Diffie-Hellman and RSA, that, especially Diffie-Hellman, this is an efficient calculation. And what you do is you take this number and compute it. It'll take, like, you can do it in polynomial time, in basically logarithm of the size of this number, log P, steps. And you get a number that's either 0, -1, or +1 mod P, and that is this number right here. So you might like that. Just alternative definition of the Legendre symbol. It's simply that number right there. Fully computable, directly, in a very explicit way. You don't have to use quadratic reciprocity to compute this. In fact, if A is large, it would be prohibitive to factor A, but you could easily compute this. Actually, let's just try this, just to convince you. We can take our number Q from above and try to compute this to the power of Q minus 1 over 2. I'm a little scared because I haven't tried this and the number's so big, but see what happens. Remember, that one's supposed to be not a square, and that is indeed minus 1. That big thing is minus 1 mod 1, then all zeros in 4, 5, 3. And now let's do the same thing, but with 3, which is supposed to be a square. Yep. So that formula right there is yet another way of deciding efficiently whether or not a number is a square modulo p. But this comes from a completely different direction. It doesn't use quadratic reciprocity, it's more of an algorithm. And that's true because of the fact that the numbers modulo p, the non-zero numbers modulo p, are a cyclic abelian group. So, but it also kind of completely misses the surprising structure of whether or not something's a square mod p just being determined by the residue class of p. It's kind of annoying. Like you could figure out this algorithm, answer the question efficiently, but you completely miss some incredibly deep pattern. And you can't, even once you know this, it's still very hard to prove. It just doesn't at all give you the quadratic reciprocity law. Okay? So let's see, how are we doing on time?
5 minutes.
Oh, really? Okay. Okay, so let me state some things. First, the Legendre symbol is a group homomorphism. What that means, again, is that if you define psi to be the Legendre symbol with p, and you look at the non-zero elements modulo p, then it's a homomorphism. So psi of a times b is psi of a times psi of b. That's all it is. Homomorphism just means multiplicative, more or less. This is kind of obvious if you have the equivalent formulation of the Legendre symbol that I just mentioned, namely that a over p is a to the power of p minus 1 over 2. But you can prove this directly from the definition, and we're going to aim at that in a minute, or actually in a week after the weekend. It's not surprising that you have this multiplicativity because a times b to the power of p minus 1 over 2 is a to the power of p minus 1 over 2 times b to the power of p minus 1 over 2. So it's not surprising you have this. But it allows you to use quadratic reciprocity to understand a over p, assuming you factor a. And then a theorem, which I've now stated like 50 times today, the group Fp star is cyclic. That is, there's an element G in Fp star such that every single element in G is in Fp star is in the power of G. Okay? So you take any prime P at all, and there will be a number that generates it. And just to get a sense of this, if you take the number 3, this command tells whether or not 3 generates the numbers mod P. So 3 does generate the numbers mod 5. What that means is if you take the number 3 and look at its multiplicative order, that is you look at 3, 9, 27, always reducing mod 5, then you'll get all the numbers mod 5 except 0. Right? Like 3, and then you square it, you get minus 1, which is 9. Now you multiply it, so we have 3 and 4 now, and then we multiply that by 3, and you get 2. Yep, 2. So now we have 3, 4, and 2. And then you multiply 2 by 3 and you get 6, which is 1. And now we have 4 different things. So we've got everything mod 5. Likewise, 3 generates mod 7. 3 generates mod 17. It generates mod 19. It doesn't generate mod 23, but it does generate mod 29. It's actually kind of striking. Look how often 3 is a generator modulo p. So I'm just showing you that. It frequently is, as you can see here. Which, I have to state an open problem. It is an unsolved problem to prove that there are infinitely many primes p so that 3 generates. So this list, which clearly goes on forever, I mean, look, if I make this 2,000, are you at all surprised that the list gets longer? No. If I make it 4,000, it's going to get longer. The fact that this keeps getting longer is an unsolved problem. Nobody knows how to prove that. Surprisingly enough. It's a conjecture. If you want to read more about this problem, it's called Arden's primitive root conjecture. And in fact, it's not just for 3. Take any number, any positive integer that's not a perfect square, and it's supposed to be a generator of Fp star for infinitely many different primes. But there's not one number for which that's been proved. However, if you could prove the generalized Riemann hypothesis, then you would get this. But without the generalized Riemann hypothesis, which we don't know how to prove, you don't have this. So it's conjectured at least. Yes?
Is that the same Arden who's written
Yes.
modern algebra?
Wait, maybe not. There's an Arden and then there's Arden's son, who's
Oh.
a professor at MIT. And I think maybe Arden's son wrote the modern algebra book.
Oh.
But I don't think Arden made this conjecture. I mean, sorry, I don't think Arden's son made this conjecture. Obviously, Arden made this conjecture. Yeah, there's two Ardens who are both mathematicians. But the older Arden is the more number theoretic one, and the younger one is more of an algebra guy. So I think, yeah. And I've talked to the younger one about math stuff, about number theory stuff, but not the older one, because I think the older one's still alive. Okay, so let me just tell you a little bit about what the plan is next, since we're about out of time. So what I'm going to do right at the beginning next time on the whiteboard, unless next time is when Dan's speaking, which I don't think it is. I think he's speaking later in the week.
I think that's Wednesday.
Yeah, I'm going to prove that FP star is cyclic. Okay? It's in chapter 2, but I'm going to prove this. And then after that, I'll tell you why psi is a homomorphism, though I more or less did already. So that's the first thing we're going to do next. So you'll finally know why FP star is cyclic. And once we have this, then we'll start proving Gauss's law of quadratic reciprocity. And then I'll also, if we have time, say something about the problem of explicitly computing square roots modulo p, and how that is surprisingly hard. Okay, done. Have a good weekend.